deionizable energy, then I will show you that we find some analytical solutions when we consider 1, 2, or 3 levels, and we can find semi-analytic solutions when we include an arbitrary number of levels. Okay? So this was a very surprising part of this research. We never thought that we can include an arbitrary number of the levels into the quark model. Then at the end, the presentation will be quite schematic. We will show you how we include gluons. The intention is to try to solve QCD, including quarks and gluons. And then some conclusions will be drawn.
Well, let me get first
back. First, the motivation. We know that the model or the theory which is used to describe low energy QCD is normally the Desgage theory. The Desgage theory calculates observables like energies and so on from basic principles. But it has several problems. First, large numerical volume. Then, when you include quarks, it is the Fermat-Lapin problem, which you cannot get rid of, or there are some ways to put it on the side. But it's a very serious problem. It has to do with the fact that we work in the box. Then, some problem which is normally not mentioned is how to identify states. For example, we work in a box. So when we calculate the states are a representation of the QB group. There are only finite number, 5, I think, of representations. So for example, the ground state with L equal to 0 for gluons is 0, so it's in the symmetrical representation. That's fine. But in the moment we go to higher states, they decay in several representations of the QB group and even the multiplicity. So at one point, you are not able to identify all the representation of the QB group which belongs to a given spin. And then you have problems of identification of states. So you don't get a complete spectrum, and you have a problem of identification of states. And when you get finally spectrum or some estimation of the spectrum, you cannot understand in the Desgage theory why the level on is as it is. And we showed it in 1 or 10 years ago in the case of gluons. So we want to develop a theory or method to solve QCD at low energy as well as Desgage theory by using many model techniques. Or at least we want to see how far we can get with it, because it's not really a problem. Another way to treat QCD at low energy we saw in the last first 2 talks is you can use phenomenological models, methods of proof theory. All these kind of models are very elegant and get very nice reproduction of experimental data, but they are not microscopic. So one motivation is when we develop a theory which treats QCD at low energy with metabolic techniques, which use the same kind of language, maybe we can derive the structure of phenomenological models, or we can tell them how these phenomenological models have to be constructed. So what are the basic ingredients? The basic ingredients, we use SU3 color. In former presentations I gave here, we used SU2 color for simplicity, but now we use SU3 color. We use SU2 flavor, only up and down quarks, but that's not really a restriction. We can easily add strange quarks, charm quarks when we want to do that. At a certain point, there are some changes in the Hamiltonian, but we can solve it. Then we use a Dirac picture. Normally in particle physics, one talks about quarks, antiquarks, all have a positive energy, but we use a Dirac picture. We only work with quarks, and antiquarks are given by holes, the low energy. And both ways to treat them, quarks and antiquarks, are equivalent. We can show it very easily. Then, in the first part of the talk, I will exclude gluons. Gluons are not dynamical. So want to see how we can improve gluons dynamically. The biggest restriction, which makes this presentation still half phenomenological, is we have a finite volume yet. And the reason of that is that in order to increase the volume, we have to include further interaction terms, which are given in the Hamiltonian. And once we take them into account, then we can release the limit of finite volume, and we are able to see. The basic ingredients are Feynman equation relation operators. The quantum numbers are really this one, decoupled form, coupled form. We use it as a basis, an oscillator. We can use any kind of basis. It doesn't mean that we have the model of the harmonic oscillator, because we take all states into account. N is the positive quantum number, L is the orbital spin, J is the total spin, L is projection, and C is the component of color, F a component of flavor. Alpha here in front can be plus 1/2, minus 1/2. It means plus 1/2 positive energy level, minus 1/2 negative energy level. And that's Hamiltonian use. And this Hamiltonian is QCD. There's no approximation. Well, one approximation. This Hamiltonian at low energy. It was constructed by Adam Stepanyak and Swanson. And what they do, they start from QCD, as given by T.D. Lee, and in the Coulomb gauge. Then they use BCS transformation, type BCS transformation, a smart cut off in order to retain several symmetries. I don't understand all of that, what they do, but finally the Hamiltonian, divide the dominant part of the Hamiltonian, which defines the scale, and the interaction part. And the interaction part still can give changes of a couple of 100 GBs. So we will deal now with that part. This part, in the first part of the talk, I don't consider because it is trivial. It will just give harmonic oscillator states of the gluon. And in the paper of Adam et al., this part was picked first here. But what we did, we substitute by average potentially zero and put the difference to the interacting part. This value can be determined very easily, but you will see that it will not play a role when we want to find any solutions. The advantage of this is that this is just a color scalar of two charge interaction between two charges, and it will be a second order Casimir operator SU3. So, as I told, it will be third order Casimir operator SU3. So what it does, all states with color 0, which we consider physical states, will be at low energy. In the moment we have color, we are shifted up at very high energy. dB0 is proportional to G squared, so it's a very large number for large G. Which we expect, so we only deal with color 0 states. It's remnant of confinement. Then the rest of the part of the Hamiltonian can be written in a sum of two operators. Already in the, we use the letter K plus, K minus, because it will relate to the solutions we have found. And the K plus operator, what it does, it is given here with some well-known coefficients, I don't mention here. What it does, it annihilates quark in the lower level with a main quantum number n prime and the angular momentum J minus 1/2, and it changes to an upper state with n and angular momentum J plus 1/2. So it changes angular momentum and it changes the main quantum number. And K minus is the other one. Now when we this is illustrated here in the next picture. Here I only plotted the positive energy level states. For each positive energy state, you have a negative energy state. So K plus connects the negative P 1/2 to the positive S 1/2, or negative S 1/2 to the positive P 1/2. And we can divide this interaction in terms of columns. It only acts within one column. It doesn't interact with one column, with the other column. It only acts in one column. So when we now restrict to one level and this we showed in 2003, we got an Leak solution. But that was very trivial. All physical states that if we had take zero mass for the quarks, they generate at zero energy, and all with the color are shifted up. Then when we take two levels, and here on this I recall, I think one of the last Cognitive conferences, then we get an analytic solution, which is of the type SU2. So therefore I wrote this K plus K minus. When I calculate the commutator of those, I get an operator which is the number of quarks in the upper level minus the number of quarks in the lower level divided by 1/2. When we add the third level, or here the third level, or here the third level, so we get a whole bunch of analytic solutions. Then also the K plus, the commutator of K plus K minus gives an operator K0, which is now not just the difference of the quarks at upper level, lower level, divided by 1/2, but when I calculate K0 with K plus, K0 with K minus, I just get the SU2 algebra. So in that, this was not at all trivial, and we discussed it very much with Adam and Osvaldo, and there's no way to say from the start that QCD has this kind of structure. So in that case, where this state satisfies the SU2 algebra, this is just a Kx operator, and we can diagonalize it. We know how to do it. But we thought we can continue, and we added to the next level. It's really a large algebraic calculation. It's very broad, but then we did the next one, and there's no SU2. But the fact that we could already find here analytic solutions, we thought maybe we can find with another type of transformation diagonalization. So what we did is the following. We have to see the structure of this operator. To see this interaction mixes main quantum number and spin. So what we did first to make a unitary transformation from the oscillator state with n for fixed orbital angular momentum to new ones, which we call set of n1, k, and q, in such a way that it will be diagonal here. So it will appear operator speed diagonal b where this is already diagonal. And then we do another unitary transformation to diagonalize the respect to the orbital angular momentum. So what we do in the first step, we take a mixture of all S states, all P states, all P states, and all D states, with spin 3/2, and so on. And then we make subsequent unitary transformation. I don't present here the details because this I presented the last time, and or at least the first steps, and it's published. It was published nearly a year ago. So we get first mixing the same orbital spin. We get a condition that in order this is a factor in front of the sun that is diagonal, and it involves the solution of there are some other equations which have to do with the fact that it has to be a unitary transformation, but these are p quadratic equations. These have to be solved numerically. So what we obtain is a semi-analytic solution. But solving p quadratic equations, it's not so trivial, but it's easy to do. And then in the next step, we do a BCS transformation, which diagonalizes, not mixing, diagonalizes of the spin, and we get two gap equations, which have to be solved here. The masses of the quarks enter, but the F0, K, J minus 1/2, and so on, are not the mass of the quarks. They depend on sum of which depends on these alpha and betas and the mass of the quarks. The C is cosine and S is sine, and the angles, there are two kinds of angles. One is J minus 1/2 and one is J plus 1/2. And of course, for each K, for each new main quantum. So what we finally get is that the whole QCD Hamiltonian, at least the part we consider, has a kinetic energy, which is diagonal now, and plus a potential, which is the second order Carson operator. And these numbers, E, this